Module 4, Lecture B, Multiple Features. By the end of this lecture, you will be able to prepare multiple scaled features for a regression model using NumPy and pandas, train a multi-feature linear regression model from scratch with gradient descent, and evaluate and compare regression models using test error and visual diagnostics. Feature matrix setup. Scaled feature matrix. A scaled feature matrix stores regression inputs, so each observation is a row and each feature is a column. Scaling puts features on comparable numerical ranges, preventing large-valued measurements from dominating smaller but still important ones. This helps the model treat features more fairly and learn from the data more effectively. To build a scaled feature matrix, first choose the relevant numeric columns and clean the data by handling dates, categories, missing values, and text labels. A pandas data frame helps keep column names and makes inspection easier. After selecting the features, convert them into a numerical matrix so NumPy can perform efficient calculations across rows and columns, giving the model a consistent set of inputs. When scaling features, learn the scaling rules only from the training data, then apply the same rules to validation, test, and future data. This prevents outside information from influencing preparation and gives a more reliable estimate of model performance. Consistent scaling also ensures the model sees features in the same transformed form it learned from, which supports gradient-based learning and makes features easier to compare. Python code. Scaled feature matrix. Build a scaled feature matrix by using pandas to keep the columns readable and NumPy to handle the matrix calculations efficiently. We import NumPy for numerical work and array handling, pandas for organizing and analyzing tabular data, and Matplotlib's plotting tools to visualize and compare raw and scaled features. We create a small pandas dataset to represent civil engineering data in a structured form. It includes observations for floor area, distance, age, and monthly energy use. Organizing the data this way makes it easier to analyze and work with later. We select the key numeric features for the analysis: floor area, distance, and age. These columns are then converted into a floating point NumPy array so they can be used efficiently in later numerical and matrix operations. We choose monthly energy consumption measured in kilowatt hours as the regression target and convert it into a numeric array. We then check that the feature data has the correct shape, so each feature row matches one target value and the inputs and outputs stay aligned. To standardize the feature matrix, we first compute the mean of each feature across all samples, then compute each feature's standard deviation. The mean shows the central value, while the standard deviation shows how much the values vary. Using the population standard deviation is appropriate because the full dataset is being scaled. These values are then used to center and scale the features so they can be compared more fairly. Before scaling the data, 0 standard deviations are replaced with 1 to avoid division by 0. The features are then standardized by subtracting each feature's mean and dividing by its standard deviation. This gives the features a mean of 0 and a standard deviation of 1, which helps many machine learning algorithms work effectively. Create clear column names for the scaled features by adding the word scaled to each original feature name. Then build a pandas data frame from the scaled feature data and apply those names, so the resulting columns are easy to read and identify as scaled values. We check the raw and scaled feature matrices to make sure they have the same shape, confirming that scaling did not change the data structure. Then, we inspect the scaled columns by checking that their means are near 0 and their standard deviations are near 1, which verifies successful standardization. Finally, we look at the first scaled row as a quick sanity check of the transformed data. Set up a Matplotlib figure with two side-by-side subplots. In the first subplot, use a box plot to show the distribution of the raw feature data. Label the x-axis with the feature names and title it Raw Feature Ranges. Rotate the x-axis labels slightly to make them easier to read. The second subplot uses a box plot to show the distribution of each scaled feature, making it easier to see how scaling changed the data spread. It is titled Scaled Feature Ranges, and the feature labels on the x-axis are rotated slightly to improve readability. Using Matplotlib's tight layout command helps subplots fit cleanly within the figure and reduces overlap. The show function then displays the plots on screen, making it easier to inspect feature distributions and scaling. This script prepares a small civil engineering dataset for analysis by standardizing features such as floor area, distance, and age against monthly energy consumption. It computes each feature's mean and standard deviation, then rescales the values so they are centered and comparable, while avoiding division by 0. The output checks the raw and scaled data shapes, confirms the scaled column's summary statistics, and shows the first scaled row. Box plots then compare the feature ranges before and after scaling, illustrating how standardization makes the distributions easier to analyze. Scaled feature matrix. A scaled feature matrix stores observations as rows and features as columns, with each feature transformed to a similar numerical range. Scaling keeps the meaning of the data the same, but prevents large-valued features from dominating smaller ones during regression training. This helps the model use all features more fairly when making predictions. To build a scaled feature matrix, first choose the relevant numeric predictor columns and keep them separate from the target value. Represent the data as a two-dimensional matrix where each row stays aligned with its features. Then scale each feature column separately, since each one may have a different range and spread, helping the model compare feature changes more evenly during training. When scaling features, learn the scaling values only from the training data. Then apply the same transformation to validation, test, and future data. This prevents information from outside the training set from influencing model preparation and gives a more honest performance estimate. Keeping the input format consistent also improves computational stability before fitting a regression model. Python code Scaled Feature Matrix. Create a scaled feature matrix using only pandas and NumPy, while keeping the training and testing data separate throughout the process. We begin by importing two core libraries for data work: NumPy for numerical operations and array handling, and pandas for working with structured, table-like data. Together, they provide the basic tools needed to create data structures, manipulate data, and perform calculations. We create a small pandas data frame to store tabular civil engineering data. It includes features such as floor area, distance, age, and price, with each column holding a list of values. This structure makes the data easy to organize, manipulate, and analyze later. We add two columns to the dataset: property age in years and property price in thousands of US dollars. Age ranges from 5 to 60 years and may help explain property value. Price ranges from $310,000 to $430,000 and is the target we want to predict from the other features. To build the predictive model, we first separate the dataset into input features and a target. The features are floor area, distance, and age, which are used to make the prediction. The target is the price in thousands of US dollars, which is the value the model learns to estimate. The dataset is split into training and testing parts before scaling. The first 4 rows are used as the training data to learn the scaling values, while the remaining rows are kept as the test data. This ensures the test set stays separate and prevents data leakage. The selected feature columns from both the training and test data are converted into NumPy matrices using a float data type. This gives both datasets a consistent numerical format, making them ready for efficient processing, such as scaling. We prepare the target values by matching them to the training and testing data rows. For both datasets, the target column is extracted and converted into a floating point NumPy array. This gives the model numerical targets for training and consistent values for evaluating its predictions. We first confirm that the training and testing feature data are both 2-dimensional matrices, so they can be processed consistently. We then check that the training data has the same number of columns as the selected features, ensuring the prepared data matches the intended feature set. To standardize the data, we compute the mean and standard deviation of each feature column using only the training set. The means center the features, and the standard deviations scale them so their ranges and variances are more comparable. Learning these values only from the training data prevents information from the test set from leaking into model evaluation. To avoid division by 0 during feature scaling, any 0 standard deviation is replaced with 1. The training data is then standardized by subtracting each feature's mean and dividing by its standard deviation. This gives features a mean of 0 and a standard deviation of 1, helping many machine learning algorithms work more effectively. Scale the test data using the mean and standard deviation calculated from the training data, so both sets are transformed consistently. Then place the scaled training data into a pandas data frame with the original feature names to keep the data clear and easy to reference. The output checks that the data preprocessing worked as expected. It reports the NumPy version, confirms the shapes of the scaled training and test feature sets, and verifies that the scaled training features have means near 0 and standard deviations near 1. It also shows one transformed training row for reference, while confirming that the training target values were left unscaled. This script shows how to scale feature data correctly before machine learning. It splits the data into training and testing sets, then uses only the training set to compute each feature's mean and standard deviation. Those same values are applied to both sets, so the test data is transformed consistently without leaking information. The scaled features have mean 0 and standard deviation 1, while the target prices are left unchanged. Feature scaling basics. Feature scaling puts input measurements on similar numerical ranges, so regression models can learn more fairly. This matters when features use different units or magnitudes, such as room counts, area, or distance. Scaling helps prevent large numbers from dominating the model and lets it focus on real patterns in the data. Scaling features is important when using gradient descent for regression, because large feature ranges can make training inefficient or unstable. Putting features on comparable scales creates a more balanced optimization process and makes learning less sensitive to the learning rate. Common approaches include centering features around their average or rescaling them to a fixed range while preserving their relationships. Feature scaling is an important data preparation step in tools like NumPy and pandas. Scale each feature using parameters learned only from the training data, then apply the same scaling to validation or test data. This prevents information from future or test examples from leaking into training and gives a fairer evaluation on unseen data. Consistent scaling helps the model interpret new inputs in the same way it learned from past data. Python code, feature scaling basics. Feature scaling helps regression models handle input variables that use very different ranges. Using a small civil engineering-style dataset, we can compare the original raw inputs with their standardized versions to see how scaling centers the features and makes their ranges more comparable. This makes the data easier for many regression methods to process consistently. The script begins by importing key Python libraries for data work. NumPy supports efficient numerical operations and arrays. Pandas helps manage and analyze structured data. And Matplotlib's plotting tools create visualizations. Together, these imports prepare the script for data processing and visualization. We create a small fixed dataset of bridge characteristics using a pandas data frame, a standard Python structure for tabular data. The dataset includes bridge span length, deck width, age, and average daily traffic in thousands of vehicles. This simple structured data will be used to demonstrate feature scaling techniques. We select the key bridge features needed for analysis: span, deck width, age, and daily traffic. These columns are taken from the dataset and converted into a floating point NumPy array, making the data consistent and ready for numerical processing such as scaling. We check the feature matrix dimensions to make sure the data was converted correctly. The number of rows should match the bridge data entries, and the number of columns should match the feature names. This validation helps catch any structural errors before using the matrix. Feature scaling starts by finding each feature's mean to center the data. Then its standard deviation to measure how much values vary. These statistics are used to normalize the features so they have more consistent scale and variance, which can improve the stability and performance of machine learning models. To avoid division by zero during feature scaling, zero standard deviations are replaced with 1 using NumPy's where function. The data is then standardized by subtracting each feature's mean and dividing by the safe standard deviation. This gives features a mean of 0 and a standard deviation of 1, helping many machine learning algorithms work more effectively. Create a new data frame from the scaled features using the original column names so the results are easy to inspect. Then compare the spread of each feature before and after scaling by finding the difference between its maximum and minimum values in both the raw and scaled data. This shows how scaling changes the range of the features. We check the raw and scaled feature matrices to confirm they have the same shape, meaning scaling did not change the data dimensions. Then we compare feature ranges before and after scaling to see how the spread has been standardized. Finally, we verify that the scaled features have means close to 0 and standard deviations close to 1, confirming successful standardization. A figure is created with 2 side-by-side subplots to visualize the data. The first subplot shows a bar chart of the raw feature ranges, using feature names on the x-axis and range values as bar heights. The bars are colored steel blue. The chart is titled Raw Feature Ranges, and the x-axis labels are rotated for easier reading. This part shows the feature ranges after scaling, using a bar chart in the second subplot. Each bar represents one feature's range, with dark orange coloring for clarity. The chart is titled Scaled Feature Ranges, and the x-axis labels are rotated to make them easier to read. To finish the comparison, Use Matplotlib's tight layout function to clean up the spacing between subplots. Then display the plot so the raw and scaled feature ranges can be compared side by side. This script shows how feature scaling standardizes bridge data, such as span, deck width, age, and traffic. It calculates each feature's mean and standard deviation, then rescales the values by subtracting the mean and dividing by the standard deviation, with a safeguard against division by 0. The output compares raw and scaled summaries, showing that features with very different original ranges become more consistent after scaling. A bar chart then visually reinforces how scaling changes the feature ranges. Gradient descent loop. Vectorized predictions. Vectorized predictions let a regression model process the whole dataset at once, instead of one observation at a time. Each row represents an example, each column represents a feature, and the model combines all feature values with their weights to produce one prediction per row. This makes prediction faster and fits naturally with how modern data tools organize and process data. Vectorized predictions make model training faster by processing the full feature matrix and all model weights at once, instead of using slow step-by-step loops. For example, a model can predict prices for thousands of cars simultaneously by combining each car's features with the learned weights. This efficiency is especially important in gradient descent, where predictions must be updated repeatedly, making large datasets practical to train on. Vectorized predictions let a model make predictions for the whole dataset at once, then compare them with the true values during gradient descent. This helps reveal overall error patterns, especially in regression with multiple interacting features. By using all data together, vectorization makes training faster and supports more reliable model improvement. Python code, vectorized predictions. Vectorized prediction uses many feature columns at once, such as scaled civil data, to make model calculations more efficient. During training, gradient descent updates all the weights together. The script imports 3 core Python libraries for data work: NumPy for efficient numerical operations and arrays, pandas for managing and analyzing data with data frames, and Matplotlib's plotting tools for creating visualizations. Together, these libraries support data manipulation, analysis, and visualization. Setting the random seed to 7 makes the script generate the same random numbers each time it runs. This reproducibility is important for debugging and for comparing results across runs. We create a small bridge inspection dataset using a pandas data frame. It includes bridge span length, age, average daily traffic, and repair cost, allowing us to explore how these bridge features relate to repair expenses. We choose span, age, and traffic as the model's input features, then convert those columns into a floating point NumPy feature matrix. The repair cost column is converted the same way to create the target values the model will learn to predict. We check that the feature data has 6 rows and 3 columns, confirming it was prepared in the expectant structure. We also confirm that the repair cost targets contain 6 values, so each feature set has a matching target for analysis. To standardize the feature matrix, compute the mean and standard deviation of each feature column, then subtract the mean and divide by the standard deviation for each feature. This gives every feature a mean of 0 and a standard deviation of 1. Standardization helps gradient descent work more effectively. To prepare data for linear regression, add an intercept column made of 1s to the scaled feature data. This lets the model learn a baseline prediction when all features are 0. Combining this column with the features creates the design matrix, so gradient descent can update the intercept and feature weights together. The model begins with all weights set to 0, including the intercept and feature weights, giving gradient descent a neutral starting point. A learning rate of 0.08 controls the size of each weight update, balancing speed and stability. The gradient descent process then runs for 300 iterations, so the model can learn from the data. Gradient descent repeats a simple update process for a fixed number of iterations. The model first predicts repair costs using the current weights, then compares those predictions with the actual costs to find the errors. It uses these errors to compute a gradient, which shows how the weights should change to reduce the cost. The weights are then adjusted by moving a small step in the opposite direction of the gradient, gradually improving the model over time. Predictions are made by multiplying the design matrix by the weights to estimate repair costs. To measure accuracy, we compute the root mean square error by comparing predictions with actual costs, averaging the square differences, and taking the square root. A lower RMSE means the model's predictions are closer to the real data. The output checks that the NumPy version and model dimensions are correct, including the design matrix and matching weights vector. It then shows the first few rounded predictions to preview model behavior and reports the training root mean square error in $1,000 as a compact measure of repair cost prediction accuracy. This plot compares actual repair costs with the model's predicted repair costs after gradient descent. A scatter plot shows actual values on the horizontal axis and predicted values on the vertical axis, with a dashed diagonal reference line marking perfect predictions. Axis labels, a title, and a light grid make the chart easier to interpret, helping us visually judge how closely the predictions match the real data. This script uses a small bridge inspection dataset to predict repair costs from span, age, and traffic. It scales the data, adds an intercept, and uses gradient descent to learn the model weights over repeated updates. After training, it reports key outputs such as matrix shapes, sample predictions, and root mean square error in thousands of dollars. A scatter plot of actual versus predicted costs with a perfect prediction reference line provides a quick visual check of model performance. Weight updates. In gradient descent, weight updates are how a model learns from prediction errors. Each weight is linked to a specific input feature, and the model adjusts it based on how that feature contributes to the error. These changes follow the direction of the error, allowing the model to make small, targeted improvements instead of random adjustments. In vectorized gradient descent, all weights are updated at the same time, which is important when a dataset has many features. Each update changes weights according to how strongly each feature relates to the prediction errors. So more influential errors lead to larger adjustments. The learning rate controls the size of these changes. If it is too high, training can become unstable, and if it is too low, learning becomes slow. The bias term sets a model's overall prediction level, while feature weights control how each input affects the result. If a model consistently predicts too high or too low, adjusting the bias corrects that general offset, such as an incorrect baseline in rent estimates. With well-scaled features and a suitable learning rate, updating both bias and weights helps reduce errors and improve the model over time. Python code. Weight updates. Show how vectorized weight updates work using scaled civil engineering features. Then compare the model's errors before and after the update to highlight the improvement. We import 3 core Python libraries for data work: NumPy for efficient numerical operations and arrays, pandas for manipulating and analyzing tabular data, and Matplotlib's plotting tools for creating visualizations. Together, they support data handling, computation, and presenting results visually. Setting NumPy's random seed to 7 makes the script generate the same random numbers each time it runs. This makes results reproducible and helps with debugging. We create a small pandas dataset of bridge construction costs, organized as a data frame. It includes span length, deck width, traffic volume, and cost for several bridge projects. This structure makes the data easy to analyze and prepare for modeling. To prepare the data for bridge cost prediction, we use span, deck width, and traffic as the input features, because they are relevant to cost. These columns are converted into a numeric input matrix, while the cost column is converted into the target values. This creates the basic dataset needed for later processing and model training. Check that the feature data and target values align correctly. The feature matrix should have 1 row for each target value, and its number of columns should match the listed feature names. These checks confirm that every example has a target, and that all intended features are included. To standardize the input data, we first find the average and standard deviation of each feature column. Then each feature value is adjusted by subtracting its column average and dividing by its column standard deviation. This centers the features around 0 and gives them a standard deviation of 1. Helping each feature contribute more evenly during model training and gradient descent. We initialize the linear model by setting all feature weights and the bias to 0. The learning rate is set to 0.08, which determines how large each gradient descent update will be, and helps balance faster learning with the risk of overshooting the minimum. This function measures prediction accuracy using mean squared error. It compares the model's predictions, including the bias, with the actual target values, squares the differences, and averages them. The result is one number that shows how far the predictions are from the true values on average. Before training begins, we calculate the initial loss using mean squared error. This compares predictions from the starting weights and bias with the actual target values, squares the errors, and averages them. The result gives a baseline for judging whether learning improves the model. The loop runs 120 gradient descent steps to improve the model. In each step, it predicts costs using the current weights and bias, compares those predictions with the actual costs, and measures the errors. It then computes gradients for both the weights and the bias, showing how each should change to reduce the error. Finally, the model updates its parameters in the direction that improves accuracy. In gradient descent, the model updates its weights and bias by moving them slightly in the direction that reduces error. Each update subtracts the learning rate times the corresponding gradient from the current value. Repeating this process gradually improves the model's predictions. After training, we use mean squared error again to check how much the model has improved. The final predictions are then found by combining the input features with the learned weights and adding the bias, giving the updated cost estimates. The output first shows the NumPy version to support compatibility and reproducibility. It then compares the model's mean squared error before and after training to show improvement. Finally, it reports the learned feature weights and bias, which indicate how the trained model fits the data. This plot compares actual costs with predicted costs from a multi-feature gradient descent model. Actual costs are shown on the horizontal axis, predicted costs on the vertical axis, and each point represents one prediction. A dashed reference line shows where perfect predictions would fall, making it easy to judge how closely the model matches the real values. Labels, a title, and a light grid make the visualization clear and readable. This script uses linear regression with gradient descent to predict bridge construction costs from features such as span, deck width, and traffic. It scales the data, starts with zero weights and bias, then repeatedly updates them to reduce mean squared error. After training, it compares the initial and final errors, reports the learned parameters, and plots actual versus predicted costs to show the model's fit. The example also demonstrates how vectorized NumPy operations make the calculations efficient. Loss tracking. Loss tracking records how well a model performs at each training step. In regression, it shows how far the model's predictions are from the actual values as the weights are updated. Storing these losses creates a learning history, making it clear whether gradient descent is improving the model. Early in training, a healthy loss pattern usually trends downward as the model adjusts its weights and reduces prediction errors. The decrease may not be perfectly smooth, especially with larger learning rates or data subsets, but the overall direction should show learning. If the loss stays flat, the model may not be improving, and if it spikes, the updates may be too aggressive or the data may need better scaling. Tracking loss during training shows whether a model is still improving and helps guide when to stop. If loss levels off, more training may add little value, while falling training loss, combined with worse results on new data, can signal overfitting. Monitoring loss makes it easier to debug training, compare models, and avoid models that fit past data but fail in real-world conditions. Python code, loss tracking. During gradient descent, track the loss to monitor how learning improves over time. Use scaled civil engineering features so the optimization behaves more reliably, and plot the learning progress clearly to make the training trend easy to interpret. We import 3 core Python libraries for data work: NumPy for efficient numerical operations and arrays, pandas for manipulating structured data, and Matplotlib's plotting tools for visualizing data and results. We set NumPy's random seed to 42, so the script produces the same random numbers each time it runs. This makes the results consistent and reproducible. We create a small simulated housing dataset with 80 samples. For each house, we generate square footage, age, and distance to public transit using normal distributions that reflect typical variation in these features. These simulated inputs will later be used to model housing prices. The target housing price is modeled in thousands by combining key features with random variation. A base price of 55 is adjusted upward based on home area and downward based on age and distance from transit. Random noise with mean 0 and standard deviation 18 is added to reflect real-world price variability. A pandas data frame organizes the dataset by storing features such as area, age, and distance to transit alongside the target value, price in thousands. This makes the data easier to analyze and manipulate with pandas tools. We prepare the data by selecting the input features from the data frame: area, age, and distance to transit. These become a two-dimensional array, where rows are samples and columns are features. We also extract the target, price in thousands, and reshape it into a column vector so it is ready for later matrix operations. The code checks that the prepared data has the expected dimensions before any further work. It confirms the feature matrix has 80 samples and 3 features, and that the target values match the same 80 samples. These checks help catch data shape errors early. Feature standardization helps gradient descent update more smoothly and reliably. For each feature, we center the data by subtracting its mean, then scale it by dividing by its standard deviation. This puts features on a similar scale, which can improve convergence speed and stability. To prepare data for linear regression with an intercept, add a column of ones to the scaled feature matrix. This column represents the constant term in the model. Combining it with the features creates a complete feature matrix, where each row is a data point and each column is a model input. The model begins with all weights set to 0, including an extra weight for the intercept. A small learning rate of 0.08 controls how much the weights change during gradient descent, helping keep training stable. The algorithm runs for 120 epochs, and the loss from each epoch is stored, so performance can be tracked over time. For each training epoch, the model uses the current weights to generate predictions from the feature data. It then compares those predictions with the actual target values to find the errors. The mean squared error is calculated as the loss, and this value is saved so the model's performance can be tracked over time. To perform one step of gradient descent, we first compute how the loss changes with respect to the weights using the feature data and the current errors. This gradient shows the direction and size of the needed adjustment. We then update the weights by moving them slightly opposite the gradient, scaled by the learning rate, to reduce the loss. The output first checks the NumPy version to support compatibility and reproducibility. It then compares the starting and final mean squared error from gradient descent and reports the difference between them. This loss reduction shows how much the model improved during training. This plot visualizes how the mean squared error changes during gradient descent. A new figure is created. The loss history is drawn as a clear navy line, and the axes are labeled by epoch and mean squared error. A title, subtle grid, and adjusted layout make the chart easier to read before it is displayed. This script demonstrates gradient descent on a synthetic housing dataset. It creates sample features and noisy price targets, scales the data, adds an intercept, and starts the model weights at 0. Over 120 training epochs, it updates the weights, records the mean squared error, and shows how the loss falls from its initial value to its final value. A loss plot then visualizes the model's learning progress over time. Comparing regression models. Test error comparison. Comparing test errors helps determine which regression model is likely to perform better on new data. A model may fit its training data well, but the test set shows whether it can generalize beyond what it has already seen. In practice, test error is a key measure of how reliable a model's predictions are in real-world use. To compare regression models fairly, calculate test error the same way for each model, using the same test set, preprocessing, and error metric. If a model with more features has lower test error than a simpler one, those features likely improve predictions on new data. Training error alone is not enough because complex models can fit past data well without performing reliably in real settings such as healthcare or finance. Test error should be judged in the context of the prediction task. The same error may be acceptable in a variable setting, such as cafe sales, but unacceptable when high precision is required, such as medication dosage. compare models using both statistical performance and practical consequences, focusing on how well they work on new data and fit the real decision. The best model is not always the most complex, but the one that is reliable and appropriate for real use. Python code, test error comparison. Compare regression models by evaluating their test error, using scaled civil engineering features for fair training. Build simple models from scratch to understand how their performance differs. This line means the script only uses standard Python libraries, so no extra packages need to be installed. In a typical Python environment, everything required to run the code is already available. We begin by importing 3 core Python libraries for data work: NumPy for numerical operations and arrays, pandas for working with tabular data, and Matplotlib's plotting tools for creating visualizations. We use NumPy's default random number generator with a seed of 42, so it produces the same random sequence every time the code runs. This makes results reproducible, which is important for testing and comparing models consistently. We create a synthetic dataset of 80 bridges to support later analysis. For each bridge, we randomly generate a span between 10 and 80 meters, an age between 1 and 60 years, and average daily traffic between 2 and 45,000 vehicles. These ranges produce a varied dataset that represents different bridge sizes, ages, and usage levels. Random noise is generated with an average of 0 and a standard deviation of 18 to mimic real-world variation. The synthetic inspection cost, measured in thousands of dollars, starts from a base value of 40 and increases with span, age, and traffic. Adding the noise makes the final cost data more realistic and less perfectly predictable. A pandas data frame is used to organize the dataset into a structured table with columns for span, age, traffic, and cost. This makes the features and target variable easier to manage and analyze, preparing the data for machine learning tasks such as training and testing regression models. The data is shuffled before splitting, so the training and test sets are random. All rows are kept but reordered, and a fixed random seed makes the shuffle reproducible. The index is then reset, so the shuffled data has a clean sequential order. The data is split into a training set and a test set by using 75% of the rows for training and the remaining rows for testing. Each subset is copied, so changes to it do not affect the original data. This lets the model learn from one portion of the data and be evaluated on separate unseen data. This feature scaling function standardizes selected columns using statistics from the training data. It computes each column's mean and standard deviation, replacing any 0 standard deviation with 1 to avoid division by 0. Both the training and test data are then scaled with the training mean and standard deviation, converted to NumPy arrays, and returned for model training and evaluation. This function uses gradient descent to fit a linear regression model. It first adds an intercept column to the features and initializes all weights to 0. For each training epoch, it predicts values, computes the mean squared error gradient from the prediction errors, and adjusts the weights using the learning rate. After all updates, it returns the optimized weights. This prediction function uses a linear model to estimate outputs from input features. It first adds a column of ones so the model can include a bias term, then multiplies the augmented feature data by the weights. The result is the set of predicted values for the inputs. The evaluation function scales the selected training and test features so gradient descent can work effectively, then extracts the inspection cost targets. It checks that the training data and target values align, fits a linear regression model using gradient descent, and uses the learned weights to predict test inspection costs. Finally, it measures accuracy with mean squared error and returns both the error and the predictions for further analysis. We compare two regression models for predicting bridge inspection costs. One model uses only bridge span, while the other uses span, age, and traffic. For each model, the evaluation function returns the mean squared error and test set predictions. Comparing these errors shows which model performs better on unseen data. The output reports the NumPy version and the size of the held-out test set to support reproducibility and evaluation context. It then compares mean squared error for two models, one using only bridge span and another using span, age, and traffic. The model with the lower mean squared error is considered better at generalizing to unseen data. A new plot is created to compare actual inspection costs with predictions from two models. One scatter plot shows results from a single feature model, and another shows results from a multiple feature model, both with partial transparency to make overlapping points easier to see. This lets us visually compare how well each model matches the actual costs. To show perfect predictions, we add a dashed reference line where predicted costs would exactly match actual inspection costs. The line is drawn from the lowest to the highest value across the actual costs and both model predictions. This gives a clear visual benchmark for judging how close each model's predictions are to the true values. The plot is made easier to interpret by labeling the horizontal axis as actual inspection cost and the vertical axis as predicted inspection cost, both in $1,000. A clear title, Test Error Comparison, explains the purpose of the chart, and a legend distinguishes the data series, such as one-feature and multi-feature model predictions. We use Matplotlib's tight layout function to clean up the plot spacing and prevent elements from overlapping. Then we display the plot, making it easier to visually compare predicted inspection costs with the actual values. This script compares two simple linear regression models for predicting bridge inspection costs from synthetic data. After generating and scaling data for bridge span, age, and traffic, it trains one model using only span and another using all three features. Both are tested on unseen data using mean squared error, and the multi-feature model usually performs better. A predicted versus actual cost plot and the printed test errors show how adding relevant features can improve regression accuracy. Prediction error. Prediction error shows how far a model's predictions are from the real outcomes, making it a key measure of performance. Beyond comparing overall test error, it is important to inspect individual errors for patterns. If errors are systematic rather than random, they may reveal problems such as missing features, poor scaling, or unreliable predictions in real-world use. Prediction error should be understood not only by how large it is, but also by where and why it occurs. In complex regression tasks, a model may perform well in some parts of the feature space and poorly in others, such as different delivery routes or unusual student study patterns. Looking at errors in context helps reveal when a model is reliable for specific decisions and when it may need improvement. Prediction error helps compare regression models beyond a single average score. A model with a slightly higher average error may still be better if it avoids extreme mistakes or performs more consistently in important situations. By examining where errors occur, such as unstable hospital predictions or weak retail forecasts during holidays, we can choose the model whose mistakes are most acceptable for the task. Python code. Prediction error. Compare prediction errors across regression models using scaled civil engineering features. Visual diagnostics can help reveal systematic mistakes in the models. The script imports 3 key Python libraries for data work. NumPy supports efficient numerical operations and arrays. Pandas helps manage and analyze tabular data. And Matplotlib's plotting tools create visualizations. Together, these imports prepare the script for data manipulation, analysis, and visualization. We initialize NumPy's random number generator with a fixed seed of 42, so it produces the same random values every time the code runs. This makes experiments and tests reproducible. We create a synthetic bridge dataset with 80 data points. Each bridge is assigned random values for span, age, and traffic load, using realistic ranges to represent variation in bridge characteristics. The target load rating is simulated by starting from a base value and adjusting it for key factors. Longer spans and older structures reduce the rating, while higher traffic increases it. And an added interaction captures the combined effect of span and age. Random noise from a normal distribution is included to make the data more realistic. We organize the bridge data in a pandas data frame, combining the input features with the target load rating. The features include bridge span, age, and traffic level. This structure makes the data easier to manage, analyze, and prepare for further work. The dataset is divided into training and testing sets. The first 60 rows are copied for training, and the remaining rows are copied for testing, so the original data stays unchanged. This split lets the model learn from one portion of the data and be evaluated on unseen data to check how well it generalizes. We define 2 feature sets to compare regression models for predicting bridge load ratings. The simpler model uses only bridge span, while the more complex model uses span, bridge age, and traffic load. This lets us test whether adding more input information improves prediction performance. To standardize the span, age, and traffic features, we calculate their mean and standard deviation using only the training data. The mean centers each feature around 0, and the standard deviation scales each feature to have a standard deviation of 1. Using only training data prevents information from the test set from leaking into the model evaluation. Before training or evaluation, the process checks that scaling values are positive and that both the training and testing datasets contain data. These safeguards prevent invalid scaling and catch empty datasets early, avoiding errors later in the workflow. To build a scaled design matrix with an intercept, first standardize the selected features using the training data mean and standard deviation. This gives each feature a mean of 0 and a standard deviation of 1, which helps many machine learning models work well. Then add a column of 1s for the intercept and combine it with the scaled features, producing a design matrix ready for regression. This function trains a linear regression model with gradient descent. It starts with 0 weights, then repeatedly measures prediction error, computes the gradient from the input data and targets, and adjusts the weights using the learning rate. After the chosen number of steps, it returns the learned weights. We prepare design matrices for both training and test data in a consistent way. For the single feature model, we scale the span feature using the training set's mean and standard deviation, then add an intercept column. We repeat the same process for the multi-feature model using span, age, and traffic, again relying on training data statistics. This ensures both models receive properly scaled inputs for training and testing. We extract the load rating values from both the training and testing data and convert them into arrays. The training values are used to teach the model, while the testing values are kept separate to evaluate its predictions. This separation helps measure model performance on data it has not learned from. We train both regression models with gradient descent. The one-feature model and the multi-feature model each start with 0 weights, then repeatedly update those weights using their training data to reduce prediction error. We generate test predictions for 2 models, one using only span and another using span, age, and traffic. For each model, we compare the predicted load ratings with the actual test values to calculate prediction errors. These errors provide the basis for evaluating and comparing model performance. To compare the one-feature and multi-feature models, we calculate 2 error measures for each, the mean absolute error and the maximum absolute error. The mean absolute error shows the typical size of the prediction errors, while the maximum absolute error shows the largest single mistake. Together, these metrics compare both average performance and worst-case error for the 2 models. The output first reports the NumPy version to support reproducibility, then compares 2 regression models for predicting bridge load ratings. It shows the average prediction error for both the one-feature and multi-feature models, followed by each model's largest error. Together, these results give a quick view of typical accuracy and worst-case performance for the 2 approaches. This plot compares prediction errors for 2 bridge load rating models on the test data. It shows actual load ratings on the horizontal axis and prediction error on the vertical axis, with a 0 error reference line to make deviations easy to see. Separate scatter points and a legend distinguish the one-feature model from the multi-feature model, allowing their errors to be compared directly. This script compares prediction errors from 2 linear regression models trained on synthetic bridge data. It creates bridge features, splits the data into training and testing sets, scales the features, and trains one model using only span and another using span, age, and traffic. After making test predictions, it reports mean absolute error and maximum error for both models. The multi-feature model usually performs better, and an error plot helps show where each model's predictions differ most from the actual load ratings. Visual model diagnostics. Visual diagnostics help reveal how a regression model performs beyond a single average error score. By comparing predicted values with actual values, we can see whether predictions follow the ideal diagonal pattern or show systematic problems. If errors grow or appear in certain ranges, such as luxury apartments in a rent model, the model may be missing important features and may be less reliable there. Residual plots help diagnose model problems by showing errors directly. When residuals are plotted against predictions or features, they should look like a random cloud around 0. Clear patterns such as curves or increasing spread suggest the model may be missing structure or have inconsistent error variance. For example, a healthcare model might look accurate overall, but still underestimate recovery times for older patients. Visual diagnostics help compare regression models by showing patterns that overall error scores can hide. 2 models may have similar average performance, but one may make large mistakes for certain groups or situations. By revealing bias, uneven errors, and unreliable regions, visual checks complement numerical metrics and support choosing the model that is most trustworthy in real use. Python code, visual model diagnostics. Visual diagnostics help reveal how a model is behaving beyond a single error score. Residual plots can expose hidden patterns, and test error is easier to interpret when viewed in context. We import 3 core Python libraries for data work: NumPy for efficient numerical operations and arrays, pandas for organizing and analyzing data with data frames, and Matplotlib's plotting tools for creating visualizations that help interpret data and model behavior. Setting NumPy's random seed to 42 makes random results repeatable each time the code runs. This supports reproducible experiments and easier debugging. We create a small housing dataset with 80 data points. Each house is assigned a randomly generated area between 500 and 2,500 square feet, and a random distance between half a mile and 12 miles. These features introduce realistic variation from modeling housing characteristics. The housing price model starts with a base price, then increases with area and decreases with distance. It adds a nonlinear bonus for homes larger than 1,700 square units, so bigger homes receive an extra price boost. Random noise from a normal distribution is also included to make the prices more realistic and variable. We use a pandas data frame to organize the dataset with columns for area, distance, and price. This makes the data easier to manage, analyze, and work with in pandas. We split the dataset into a training set and a test set. The first 60 rows are copied for training, while the remaining rows are copied for testing. This keeps the original data unchanged and lets us evaluate how well the model performs on data it has not seen before. To scale the square footage and distance features, first use the training data to find their mean and standard deviation. The mean centers each feature, while the standard deviation rescales it, so values are measured on a comparable scale. This standardization helps many machine learning algorithms train more effectively and converge faster. Before scaling, confirm the test data is not empty and that all standard deviations are positive to avoid division by zero. Then standardize the training features by subtracting the training mean and dividing by the training standard deviation. Apply the same training-based values to the test features, so both datasets are scaled consistently. Before fitting a linear regression model, we add an intercept column to both the training and test feature data. This column is made of ones and is placed alongside the existing features. It lets the model learn a constant bias term in addition to the feature coefficients. We add a squared version of the area feature to capture possible nonlinear effects of size. This new feature is added to both the training and test data so they stay consistent. With the squared area included alongside the original features and intercept, the model can represent curved relationships and be evaluated properly on the enhanced test data. We prepare the target data by taking the price column from both the training and test data and converting each into a NumPy array. The training targets are used to fit the model, while the test targets are used to evaluate its performance on unseen data. The training function prepares a linear model for gradient descent by starting the weights at 0, with one weight for each input feature. It also scales the target values using the larger of their standard deviation, or 1, which helps keep optimization stable. The scaled targets are then used in the gradient descent process. In each loop iteration, the model updates its weights to reduce prediction error. It first compares the current predictions with the scaled target values, then uses those errors to compute a gradient that shows how the weights should change. The weights are then adjusted by moving in the opposite direction of the gradient, scaled by the learning rate, so the next iteration can make better predictions. The function rescales the learned weights back to the original target scale. This is needed because training used a scaled target variable, so adjusting the weights by the scale factor makes future predictions match the original target units. We use a custom gradient descent function to train two regression models. One uses the basic scaled training data with an intercept, while the other adds a squared area feature. This lets us compare a simple linear model with a curved model that can capture nonlinear effects. We generate test price predictions for both models using their trained weights. The basic model uses the test features with an intercept, while the curved model uses test features that also include the squared area term. These two sets of predictions can then be compared to evaluate how well each model performs. We evaluate each model using root mean squared error, which measures how far its predicted prices are from the actual test prices. For both the basic model and the curved model, we compare predictions with the test data, summarize the size of the errors, and use the result to judge accuracy. This lets us directly compare which model predicts prices more effectively. The code reports the NumPy version for reproducibility, then prints the test root mean squared error for both the basic and curved models as dollar amounts. These values make it easy to compare prediction accuracy, while the plots help reveal differences in the model's error patterns. Residuals show how far a model's predictions are from the actual test prices. For both the basic and curved models, we calculate them by comparing predicted prices with actual prices. These errors are then used for visual diagnostics to assess how well each model performs. We create a Matplotlib figure with two side-by-side panels, so two diagnostic plots can be viewed together and compared easily. The figure is sized to give the plots enough room to remain clear. We compare model performance by plotting predicted prices against actual prices for the test data. One scatter plot shows the basic model, while another adds the curved model for comparison. The plot range is adjusted so all points are visible, and a dashed perfect prediction line shows where predicted and actual prices would match, making accuracy easier to judge. Set up the plot so it is easy to interpret by giving it a clear title, labeling the axes, and adding a legend. The title explains that the chart compares predicted and actual prices, while the axis labels show actual prices on the horizontal axis and predicted prices on the vertical axis. The legend helps viewers tell the different model predictions apart. Residuals are plotted against predicted prices to check how well each model performs. Comparing the basic model and the curved model can reveal patterns or bias in their prediction errors. A horizontal reference line at 0 shows where perfect predictions would fall, making systematic errors easier to spot. The second plot is labeled to show residuals versus predicted price. The x-axis represents the model's predicted prices in dollars, while the y-axis shows the residuals, or predicted price minus actual price. A legend is added to help distinguish any datasets or models being compared. Matplotlib adjusts the plot layout to improve spacing and readability, then displays the diagnostic plots. These plots help us visually assess model performance and residuals, giving insight into how well the models fit the data. This script compares two linear regression models on synthetic housing data with a nonlinear area effect. After splitting and scaling the data, it trains a basic linear model and a curved model that includes squared area, then evaluates both on test data using root mean squared error. It also compares predictions with actual prices and checks residual patterns. The curved model usually performs better because it can capture the nonlinear relationship. In this lecture, you learned to prepare multiple scaled features for a regression model using NumPy and pandas, train a multi-feature linear regression model from scratch with gradient descent, and evaluate and compare regression models using test error and visual diagnostics. In the next module, Module 5, we will go over none.
Thank you for your attention. See you all in the next lecture.